Welcome all to another session of Concept at Fingertips. This is Vidya, Physics faculty. Today let us learn the topic Electromagnetic Induction. So in the first half of the chapter, Magnetic Effect of Electric Current, we saw that if there is a conductor and if there is a conductor and if we pass a current I through the conductor, then a magnetic field is developed around the conductor. And the direction of this field was found out using right hand thumb rule. All these things we discussed in the first half of the chapter. So what if the reverse is possible, right? So if you have a magnetic field and a conductor, magnetic field and a conductor, is it possible to create an electric current? So electric current should be the output, and we have magnetic field and a conductor. So this is possible, and that phenomenon is known as electromagnetic induction. So this phenomenon was first discovered by Michael Faraday. He was an English physicist, and he discovered this phenomenon of electromagnetic induction. So what he found out was, he discovered that if you moved a magnet near a conductor, or if you moved a conductor near a magnet, then electric current was produced. So this phenomena is basically known as electromagnetic induction. So let us see the phenomenon of electromagnetic induction with the help of an activity. So in the figure, we have a coil of conductor with a number of turns, and then that coil is connected to the conducting wires and to the galvanometer. So what is a galvanometer? A galvanometer is a device to measure the electric current. So if there is an electric current passing through a circuit, then the galvanometer will deflect. And if there is no current, means the galvanometer will be at 0. And then we have a magnet as shown in the figure, a bar magnet. So at first, in the activity, what we are basically doing is we are bringing the north pole of the bar magnet towards the coil. North pole of magnet towards the coil. So what is observed is that the galvanometer had a deflection indicating a current is flowing through the circuit, and the deflection, let's say it's towards the right hand side as shown in the figure. So the observation was that galvanometer needle deflected towards right. So this indicates that there is a current flowing through the circuit. So what we can conclude is, if you bring the north pole of a magnet towards a coil, there is a induced current produced in the coil, and the current direction is indicated by the galvanometer. Now, as a second experiment, we can actually take the north pole take the north pole away from the coil. So what was observed is the galvanometer deflected in the opposite direction. So this also indicates that there is a current flowing, but this time the current flowing is in the opposite direction than the first time. So when the north pole was taken away from the coil in that direction, what happened? The galvanometer deflected in the direction opposite to that of the previous case. And also in both these cases, what was observed is that the deflection happened only as long as the movement of the coil was there. As the coil was stationary at the farther end or the near end, as the magnet was stationary, there is no deflection, or the galvanometer was at the 0. So in both cases, no deflection. When the magnet is stationary. With respect to the coil. So this is the first two set of experiments. Now the second set of experiments is like we are keeping the magnet stationary. This time we are keeping the magnet stationary and we are trying to move the coil. So that will form the third experiment, third activity. So move the coil towards the north pole of the magnet. Here in this case, we are keeping the magnet stationary. So as we can observe from the experiment, once we do the experiment, what it was observed is the galvanometer deflected towards right. And the deflection lasted as long as the coil was moving. And as the coil stopped moving, the deflection also stopped. So as a fourth experiment, what we can see is that if we move the coil away from the north pole, this time also keeping the north pole, keeping the magnet stationary. Magnet is stationary. That means magnet is at a position at rest. Now this time also the observation was the galvanometer deflected as we can already guess that the deflection will be towards the opposite direction than the First one. So deflected towards left. So both these times there was current flowing, but the current was in different directions in both these cases, right? In the first case, it was towards the right. Deflection was towards the right. So the current is flowing towards in one direction. Second case, the deflection is towards left, means the current is flowing in the opposite direction. And as we have seen in the previous for 1 and 2 experiments, in both these cases, the deflection is 0. Deflection is 0 when the coil is stationary with respect to magnet. So the same set of experiments, we can do the same set of experiments by reversing the poles of the magnet. For example, we can make this pole as the south and this as the north, and we can bring the south pole towards the coil as well as away from the coil. The whole set of experiment we can do by reversing the poles of the magnet. So in that cases also, we can see that in one time, if the current is flowing towards the in one direction, the second time it will be in the opposite direction. So this entire activity shows the phenomenon of electromagnetic induction. So what is electromagnetic induction? Electromagnetic induction is the phenomenon of inducing a voltage, inducing an EMF by changing the magnetic flux linked with the coil. Or in other words, we can say electromagnetic induction is the phenomenon of inducing a current in a conductor or a coil, in a conductor by relative motion between the conductor and the magnet. So that is electromagnetic induction. I hope the topic is clear to you. We'll meet you in another session with a new topic. Thank you.